In the previous video, we saw a bunch of conditions for a matrix to be diagonalizable. We claim that the matrix A is diagonalizable if and only if the algebraic multiplicity is equal to the geometric multiplicity, or equivalently if the sum of the geometric multiplicities is equal to n. In this video, I'll try to prove this particular statement. Let's see what might happen. So of course it's possible that the dimension of Wi is strictly less than di, in which case of course there's nothing to so it means that you cannot obtain a basis of eigenvectors for Rn, and therefore A is not diagonalizable. So when do we say that a matrix is diagonalizable? So A is diagonalizable if and only if we can find a basis v1, v2 up to vn such that each vi is an eigenvector of A. Right? If we cannot find such a basis, then A is not diagonalizable. Right? So obviously, if the dimension of Wi is strictly less than di, then it means that the sum of the dimensions is strictly less than n, and therefore A is not diagonalizable. Right? So that much is pretty straightforward. What is not straightforward is if either condition 2 or condition 3 are satisfied, then A is diagonalizable, and that is really the hard part of the proof. Right? So let's first see what may happen and what might not happen. So recall that Wi is the eigenspace corresponding to lambda I. So it is the set of all x such that A minus lambda I times x is 0. So it is basically the null space of the matrix A minus lambda I. Okay. So one thing should be clear: if I is not equal to j, then Wi intersection Wj. So what is this equal to? This is equal to the trivial space containing only the 0 vector. Right? Okay. So that is this. So basically consists of, so if you want to view it geometrically, then each Wi will either be a line or a plane, and these lines or planes are going to intersect only at the origin. There's no other intersection. Right? So suppose that we had only two subspaces, W1 and W2. Right? Let's assume that there are only two eigenvalues, lambda 1 and lambda 2. The algebraic multiplicity of corresponding to lambda 1 is d1. The algebraic multiplicity corresponding to lambda 2 is d2. Right? Now let's assume that the geometric multiplicity of lambda 1 is also equal to d1. The geometric multiplicity of lambda 2 is also equal to d2. So what can we do? We can construct a basis v1 through vd1. Right? And a basis for W2, let's call it U1 to UD2. Right? Now the algebraic multiplicities always satisfy the fact that D1 plus D2 is equal to n, and this is because the characteristic polynomial is a polynomial of degree n, and therefore D1 plus D2 should be equal to n. Right? So and every polynomial in containing every polynomial of degree n has n roots, has exactly n roots. Therefore D1 plus D2 is equal to n. And let's now assume that the geometric multiplicities are also equal to D1 and D2, and therefore D1 plus D2 is equal to n. Now the question is, does this set V1 through VD1 and U1 through UD2, right? So the union of these two sets, does this form a basis for Rn? Right? I want you to pause the video and think about this. Right? So this indeed does form a basis for Rn, because obviously the UIs don't lie in the space spanned by V1 through VDI. So the UIs are all linearly independent of the VIs, and therefore and hence they're all linearly independent of the VIs. So V1 through VD1 and U1 through UD2 all put together, this also forms a linearly independent set. And since D1 plus D2 is equal to n, it should also form a basis for Rn, because there are n, because we already have n linearly independent vectors in Rn, it should form a basis. Okay, that much is fine. So does this mean that we've already proved the theorem? Not necessarily. So let's now suppose that, so we assume that there are exactly two distinct eigenvalues, right? So now let's suppose that we have three distinct eigenvalues, lambda 1, lambda 2, and lambda 3. And corresponding to this, we have algebraic multiplicities d1, d2, and d3. So obviously, if the geometric multiplicities of any of these eigenvalues is less than the corresponding algebraic multiplicity, then we cannot construct a basis of eigenvectors for Rn, and therefore it is not diagonalizable. So let us assume that the geometric multiplicities are also equal to d1, d2, and d3 respectively. Okay. So what might happen? So we have w1, w2, and w3. So clearly, if we have a basis v1 through vd1, a basis for w2 to be v1 prime to vd2 prime, and a basis for w3 to be v1 double prime to vd2 double prime, right? So clearly the pairwise intersection is empty. So v1 through vd1 is linearly independent of v1 prime to vd2 prime. v1 to vd1 is also linearly independent of v1 double prime to vd2 double prime, right? But we are not sure about whether if we take v1 to vd1 and v1 prime to vd2 prime, we put them together, then it's possible that this set, so the set of all these vectors put together, v1 to vd1, v1 prime to vd2 prime, v1 double prime to vd2 double prime, when put together, it could become a linearly independent, it could become a linearly dependent set. Why is that the case? So for example, let's consider three vectors which are pairwise linearly independent. So one example is 1, 0. This is maybe the first set. The second set is 0, 1, right? And the third set is maybe 1, 2, right? So these two are linearly independent. These two are linearly independent, and these two are linearly independent. But when you put all of them together, they're no longer linearly independent. So such a bad thing might happen, but it turns out that this does not happen, right? So what is our goal now? Our goal is to show that if w1, if dimension of w1 is equal to d1, dimension of, in general, dimension of wi is equal to di, the algebraic multiplicity corresponding to the ith eigenvalue, then the matrix A is diagonalizable. In other words, if I take a basis v1 1 through VD1 1 union V1 2 VD2 2 V1K V2K. So if you take the union of the basis of all the eigenspaces, then this forms a basis for Rn. That is what we want to prove. Now we'll prove a slightly more general result than this. Right? In fact, we'll show. Suppose let us define the following. So W to be W1 plus W2 so on plus Wk, where Wi, where this definition W1 plus W2 so on up to Wk simply means the set of all alpha 1 x1 plus alpha 2 x2 and so on up to alpha k xk, where xi is in Wi. Right? So it's a set of all. So it is the set of all possible linear combinations of vectors from all the Wi's. Right. So this obviously forms a vector space. Claim is that if Wi's are the so clearly if there's no assumption on W1, W2 and so on, the dimension of W is in general going to be W is going to so if the Wi's are arbitrary subspaces of Rn, then the dimension of W is going to be less than or equal to K of dimension of Wi, right? But if the Wi's are the eigenspaces corresponding to the ith eigenvector lambda I, then this inequality becomes an equality. Okay, and that is what we will try to prove now. Okay, right. So what do we need to do to show that this is in fact the case? So let's suppose that suppose that this is not the case. Suppose that the dimension of W is strictly less than the sum of the dimensions of the Wi's, right? So it must mean that there is some vector in some Wi in some subspace Wi such that it can be written as a linear combinations of vectors from all the other Wj's, right? So if the dimension of W is strictly less than dimension of W1 plus dimension of W2 so on up to dimension Wk, then it must be the case that there exists some Vi in Wi or some I such that Vi can be written as alpha 1 some j not equal to I alpha j Vj for some Vj in Wj, right? Or equivalently, I mean these coefficients are not necessary because alpha j if Vj is in Wj, then alpha j Vj is also in Wj, right? So we can rewrite all of this to give the following condition. So then there exist v1, v2 up to vk such that I going from 1 through k of vi is equal to 0. Okay, so if dimension of w is strictly less than dimension of w1, dimension of plus dimension of w2, and so on, then we should be able to find vectors v1, v2 up to vk, and of course all of them cannot be equal to 0. So not all of which are 0, such that the sum of all these vectors is equal to the 0 vector. Okay, so we'll show that this is not possible. So we'll show that this cannot hold, and which obviously means that this is also not true. Right? So if we assume that this is true, then it will turn out that then we'll end up at a contradiction. Okay, so now for the sake of contradiction, let us suppose that we can find v1, v2, up to vk, where vi is in wi, the eigenspace corresponding to lambda I. So one thing to always remember is that the lambda i's are all distinct, right? So vi is in lambda I, such that the sum over all possible I of vi is equal to 0, right? So now if f is any polynomial, consider any polynomial in x, f of x, which is a0 plus a1x so on plus an x to the n, then and you take matrix polynomial f of a. If you take f of a times v, then this is equal to f of, so a times vi, then this is equal to f of lambda I times vi. We've seen this before, right? So what this means is that if you take, so since this is true, if we take f of a times sum I going from 1 through k vi, this is equal to sum I going through 1 k of f of lambda I times vi, right, which should also be equal to 0, right? Because after all, what you're doing is multiplying f of a with the 0 vector. Okay, so this is fine. So what we want to show now is that this condition is satisfied only if all the vi's are equal to 0. And to do that, we'll define the following polynomials. Right? For each I from 1 to up to k, I'll define fi of x to be the following polynomial. So it is x minus lambda 1, x minus lambda 2, all the way up to x minus lambda k, but not lambda I, so on up to x minus lambda I minus 1, x minus lambda I plus 1, so on up to x minus lambda k, right? I'll also divide this by lambda I minus lambda 1, lambda I minus lambda 2, so on, lambda I minus lambda I minus 1 times lambda I minus lambda I plus 1, and so on up to lambda I minus lambda k. So this is basically the product over all j not equal to I of x minus lambda j divided by lambda I minus lambda j, right? So I define k many polynomials, f1 of x, f2 of x, all the way up to fk of x, and each of these polynomials has the property that it is equal to 0 if x is equal to lambda j, right? For j not equal to I. Okay, so if j is not equal to I, then you will have lambda j minus lambda j in as one of these three, as one of these terms, right? And therefore fi of lambda j is equal to 0 if j is not equal to I, and it's equal to 1 if x equal to lambda I, right? Because the numerator and the denominator would be the same. For other values of x which are not lambda I or lambda j, we don't really care what happens, right? Okay, so let us take these and apply this here, right? What we get is that for each I going from j going from 1 through k, fi of lambda j times vj is equal to the 0 vector, right? And we know that if j is not equal to I, then fi of lambda j is equal to 0. So but fi of lambda I is equal to 1. So what we get, so this basically reduces to fi of lambda I times vi is equal to 0, or vi is equal to the 0 vector. So this is for any arbitrary I, and therefore what we have shown is that for all I, vi is equal to 0. So in other words, if we pick any vi, so if we pick one vector from each of the eigenspaces and sum them all, and by chance we get the 0 vector, then it must mean that each vi is equal to the 0 vector. Otherwise it's not possible. If any of the vi's are non-zero, then the sum of these vectors is also going to be non-zero. So this implies that if you pick a basis, if you take the basis of each of these wi's and take the union of all the basis vectors, then this will still be a linearly independent set, and therefore it will form a basis for W, right? So basically what we've shown is that the dimension of W is equal to the sum of the dimensions of the eigenspaces, right? So we have shown that dimension of W is equal to the sum of the dimensions of the individual eigenspaces. Now, if and in fact, one possible basis for W can be obtained by taking the union of basis for Wi. So now, if condition 2 is satisfied, then it implies then dimension of Wi is equal to the algebraic multiplicity. So the dimension of W is sum I going from 1 to n of di, but the sum of the algebraic multiplicities is always equal to n, and therefore the dimension of W equal to n, and therefore we can construct a basis for Rn using only eigenvectors, and therefore A is diagonalizable. Now also, if the sum of the dimensions of Wi is equal to n, then it also implies that we can construct a basis of eigenvectors for Rn, and therefore A would be diagonalizable.